Next up we have a slight change in the schedule. Today Greg Luerman is representing Curry Bio and he's talking about the Duchenne muscular dystrophy model.
But first,
Oh.
thank you. Totally going off of what you were just talking about, and directly to your question, can we do mechanically modify these tissues? So we mostly focus on skeletal muscle tissue. I personally have always wanted to do a tendon model for like safety pharmacology because when I was a young lad, 20 years old, I tore my Achilles tendon on ciprofloxacin. Thank you, drug industry. And have always wanted to have like a safety assessment for basically tendon stretch under these antibiotics or whatever that have been known to cause these tendon ruptures. So we actually have a model here of which we can do something similar, at least on here we're showing actually cardiac cells, but we actually run this assay to stretch these 3D tissues. Sorry, I can't find my mouse here. This is an example where we're using basically micro manipulators. This is kind of a two-post mechanism. For those in the other room who can't see me walking around, I'm pointing at the red and green dots here, whereby we keep one post stiff, the other post is either stretchable or not. But what we're seeing in these videos is we can, in this case, using what we call our Cytostretcher 3D, is do different kind of either pacing mechanisms or just pure stretch. And from a tendon model, I think we can obviously see the utility in something like that. From a neuromuscular disease point of view, that's our focus. What's really interesting for the disease state of neuromuscular disease, especially for something like Duchenne's muscular dystrophy, is a lot of genes associated with neuromuscular dystrophy are basically shock absorbers for your muscles or your tendons, right? And so if we eliminate your shock absorbers, i.e., dystrophin, that's eliminating those shock absorbers in the cells or in your tendons, your muscles. And so a lot of gene therapies have tried to replace that, and they've kind of used even miniaturized versions of this, and we're not seeing really a great functional benefit when we're putting in these miniature shock absorbers. So this is just like one example where we can create more of a physiological, clinically relevant environment to test out these different gene therapies for things like neuromuscular disease. So getting back into the original talk, what Curie Bio is focused on is trying to get these slides to work. We are located in Seattle. We're a company. We have a booth downstairs if you want to check us out. I'm missing a lot of my graphics here for some reason, but what you see on the right are a number of different animal models as well as a human clinical EMG trace. So this is an example where we're inserting a probe into somebody's wrist and stimulating the FPL muscle here. So basically a nerve conduction assay. Highly intrusive, not very high throughput, right? We can give you basically the exact same readout in one of these 3D tissues. So you're seeing this contracting here on the left, and this is a skeletal muscle tissue giving you a force frequency readout that is basically exactly paralleling what we see in these clinical EMG recordings. We can do it at scale. This is a 24-well plate. It's a non-invasive, label-free approach. We get a real-time readout. This should be flying along here in real time. There it is. Where we can look at the different contraction metrics across this 24-well plate in real time. So from a neuromuscular disease point of view, I know there's not a lot of people here doing neuromuscular disease research. From a 3D kind of organoid perspective, why these help us and help the industry and drug discovery industry in this specific disease state is really for actually this main reason right here in the middle. 2D skeletal myoblasts, when you put skeletal myoblasts on a 2D plate, they last for like a week and a half before they start to fuse into myotubes, and after they fuse into myotubes they start to become contractile. And as soon as they contract, they pop off the dish and you can't use them anymore. So when we're thinking of gene therapies take potentially months to ramp up gene expression systems are just not usable at all for a lot of these modalities out there. For 3D skeletal muscle systems and cardiac systems, we can now culture these basically indefinitely. So now that they have like 2 posts to pull against, these tissues for us have lasted many months and even up to a year in some of our clients' hands. So that's really a big one, is just the utility for more longitudinal studies, drug studies, and gene therapy studies. In addition to that, a lot of the actual disease pathology has to do with the protein's interactions with the extracellular matrix environment. Now we're getting this nice complex 3D ECM environment. The dystrophin molecule, is pulling on that 3D environment to interact with it, and this is something that we can only model in a 3D environment. We can't replicate that in 2D. And now, as I just showed you, we're also able to pull out this really clinically relevant functional endpoint, and this is going to be really the most important thing. We've seen a number of clinical trials being put on hold because there's lack of functional potency evidence in preclinical models. What that means is we put in a gene, we see gene expression, we don't know if it's going to translate or not. Does that translate to improved function? Now with these 3D models and these kind of signals which we're generating here, we can actually test, does gene expression correlate with function? So here's our fancy instrument. It's basically a magnetometer. I'm going to kind of fly through this quickly. Basically what we're doing is just simply tracking the deflection of a magnet embedded in the flexible posts, and using the magnetometers found underneath of the plate within the system, we can actually track this post in 3 dimensions. And using a very simple formula that's been around for hundreds of years, we can derive a real-time force readout from this machine. This is a 24-well system. We're able to stimulate each tissue individually with its own pacing program. So we can run a very fast, set of contractions back to back. We can run multiple tetanic contractions. We can pace these every minute of every day, or just every other day, or however we want to set up the pacing program. That can be done on this system. This is an example of what the tissues look like. They're big. They're about the size of a grain of rice, a millimeter in diameter. So we can pack a lot of cells in here. We're looking at largely like some myotubes here. They're thick enough that we can do H&E staining in the top left. We can do live cell imaging as well on these plates as well. But yeah, I wanted to get into, we're kind of missing a figure there, the dystrophin story. So I mentioned Duchenne's muscular dystrophy earlier. Up here you would have seen a nice 3D tissue showing the dystrophin staining. But the hallmark localization of dystrophin is around the myotubes. So I mentioned those myoblasts go on to form myotubes. These are the long striated structures that form your muscles. Dystrophin is a major component of that. When we knock dystrophin out using CRISPR, so we have an isogenic wild type control versus a DMD complete knockout, we see loss of that dystrophin. And then what's really important is the function, right? So now we're seeing individual contraction. We see large forces from the wild type. Those are attenuated in the DMD. And then in the tetanic stimulus, where we're basically pulling out as much force as we can out of these tissues, again, severely inhibited in the DMD tissues. I already mentioned the stretch model, and maybe I'll come back to that. The other thing that we can do is now run fatigue curves. So think of this like, if it's a mouse study, you maybe like a grip strength test or something like that, where we can actually do, in this case, like 30 contractions in a row. So just like doing bicep curls in the gym, your muscles are going to wear down. A Duchenne's muscular dystrophy patient's cells are going to wear down, or tissues are going to wear down faster. They're actually going to take longer to recover as well. Oh, this one didn't come out as all. Man, I should have really checked these before presenting these. I'll just skip through this. This is an example of basically exactly modeling a force frequency analysis done on a mouse model of Duchenne's muscular dystrophy. We get literally the exact same data coming off this in high throughput. Okay, so yeah, for the sake of time, I'll just kind of skip through this for now. I touched on this and the importance of why this is important. So again, creating more physiologically relevant, clinically relevant types of functional assessments in these tissues. So taking this one step further, we can even collect media from these stretched tissues. This is an example of a BAG3 related cardiomyopathy. So this is a cardiac construct. We're in wild type. As we stretch these, they're going to start putting out some troponin into the media. When we're comparing it against a BAG3 knockout, so a disease model, the disease model exhibits much more resistance to the stretch, and they're churning out lots of troponin into the media. Again, a clinical biomarker. All right, so I think that's largely it for the Mantarray. We also have some other cool instruments that can really, you can apply not just skeletal myoblasts or cardiomyocytes. You can apply a whole lot of other tissues onto this system. So this is our Nautilus system. It's an optical mapping platform. What you're seeing here on the left is just a standard 96 well plate. We're looking at calcium transients fluxing across each individual well. If we move on, we've really designed this platform to be very flexible for all sorts of inputs. And the advantage of this is we're getting the entire field of view. This is a 24 well plate here that we get the entire field of view at the same time. And we're seeing here individual skeletal muscle bundles firing. So we're able to stimulate those skeletal muscle bundles and pick up the calcium transient signals. So here we would see in the top the kind of force frequency analysis, and down here at the bottom we actually get extremely high temporal resolution from these constructs. So it's designed to not just pick up 2D, not just pick up these 3D muscles, but really just about anything you could put on there that's going to elicit some signal. You can think about like individual organoid bodies. You can just really dictate where you want it to pick up that signal from. So that's it. Open for questions. Feel free to stop by our booth afterwards. But yeah, thanks for your attention.
So, so this presentation is now, open for discussion. So.
Thank you for the nice presentation, and you managed even without the technical, even with the technical issues. I wanted to ask about, have you considered incorporating electrical pulse stimulation to this model, since here as well there are many companies doing one or the other, either mechanical or electrical stimulation?
Yeah, so the platform actually has on board pacing capabilities for electrical stimulation. So cardiomyocytes will beat on their own. You don't have to stimulate them. You can if you want. Skeletal muscle, if you have a truly mature tissue, should be quiescent, and that's what we see. So all the data you saw was us electrically stimulating those tissues. So that's how we can get those individual contractions. We can push them into tetanus. And skeletal muscle tissues require a lot of current. They require like 10 times the amount of current that a cardiomyocyte does to stimulate them. So we're really, we've really, turned up the gain on those to be able to stimulate those. So I should have also mentioned that the majority of our muscles use a co-culture. So we're always adding like a fibroblast or a tenocyte or some stromal population. ECM remodeling is super important for the longevity and maturity of these tissues. So that's the other point.
Thank you.
Yep. Okay.
Hi, thanks for the presentation. I was wondering if you could give us more detail about the DMD iPS cells, like the cell culture protocol, how many days you need
sure.
them to be like differentiating in the...
Yeah, so we're using a IPS-derived myoblast. So in that case, it really is going to take about a month from IPS all the way to the myoblast fate. And if anybody knows anything about this, it's actually a horribly inefficient process to create myoblasts. So we actually do a double fax sorting step once we get to that state to give us a very high, like 85% plus Desmond positive population. Once we have that, we consider that like a P1 clone. If we take those that clone out, up to about 4 or 5 passages, we can get quite a lot of myoblasts that are still very pure. If we take them out past that, they stop really having that myoblast, feature. We have to stay within that like early passage number to get really good tissues. If we go up past that, we see a direct decline in tissue force and longevity, and that correlates with like Desmond positivity as well. So a very tight QC is needed to create these really good structures that we see here.
And then how many days you do
Oh, sorry,
all
yeah.
the functional
Yeah,
analysis?
so once we get them into the myoblast fate, we just put them in at least our standard differentiation and maintenance media. That takes about 10 days to start getting the data that I was showing you here.
Okay, thank you.
Hi, maybe a little bit in addition to what was asked before. You said that you can keep your cultures month to years. Have you tested if like their characteristics stay the same over time, or how are you like maintaining this?
Yeah, we really haven't done like any RNA-seq on these kind of long-term cultures. In general, for cardiac cultures, they tend to continue to mature over some time, where their contraction rates go down, yet their forces continue to get higher to a plateau after about a month. After that, there's not a lot of changes that we're seeing, pretty static. For skeletal muscle, we see typically a plateau phase after about like 14 to maybe 20 days, where they're kind of maximally effective, and then we see some trail off, and then it plateaus about half of that max, really for the rest of their lives as well. What's been really important is the media formulation. One, we have to have those fibroblasts in there to maintain that ECM remodeling. That's super important to keep those cultures. But a lot of the standard, all of the standard 2D media for myoblasts just don't cut it. We had to completely reformulate how we're doing these myoblast cultures. So we'd be happy to talk about that more. It's a complex discussion.
Okay. So relating to that point, so the diameter of your tissue is like 1 meter or so, 1 millimeter so. So it's a very huge comparing to the normal spheroid, like 200
Right.
micrometer. So in that case, the oxygen or the nutrient go inside the organ or the
Yeah,
tissue.
great question. We don't see any we see 100% diffusion, basically. I think if they were any bigger, we might start to see issues with that. This slide here is just showing example of an AAV transduction through the tissue, and we see just really uniform expression throughout the tissue. And this is a longitudinal section, but we've seen every example on cross sections where we get really good diffusion throughout the entire tissue. So that's not an issue. We're also working on miniaturizing this as well, just so that you have to use less tissue, less number of cells. We're talking like 500,000 to 1 million cells in one of these tissues, so it's a lot.
Thank you. So last question. Okay.
Yes, just actually a question just related to this slide you just showed. So here you transduce directly the tissues from the medium. Like, how did you do it here?
Squared it on.
Okay, just quickly, just to know
Yeah.
how it works. Yeah,
Yep, very easy.
looks like there is a high efficiency.
Yeah, so what's really interesting, and this is actually really cool about the 3D tissues, is we do a lot of gene therapy services for all kinds of pharmaceutical companies. And what we found is for pretty much all AAVs, AAV6, AAV9, all the muscle-targeted AAVs with muscle-specific promoters, if you try to transduce a 2D myoblast, it takes like an MOI of like 10 to the 4th, 5th, or 6th. Lots of AAV is needed to transduce myoblasts. 3D cultures, it's 10 to the 0. Multiple folds higher expression in the 3D tissues. So our assumption is we're just getting way more muscle-specific promoter expression in these 3D tissues than you do in the precursor myoblasts. So it's really been a game changer for gene therapy research right now.
And did you try only with AAV or also other type of?
Oh, we've done every modality: exon skipping, ASOs, small molecule, large molecule, all these things work on these systems. Yeah.
Nice.
Okay, thank you.
Thank you very much.